Hi. So many people have been asking me about sine cosine encoders recently, and someone even sent me this particular PCB that they had around, and until now there has been support in the firmware that was contributed by some pull requests, and I also did some tweaks in that now and then, but I never had the chance to try it out because I didn't have an encoder. And now that I got one, I connected it and tried to get it running. And there was I think there was at least a mistake in the firmware on the fault codes for the amplitude, or for the amplitude of the square of the signals that was set a bit wrong, so I adjusted that, and after that it seemed to work fine. So we can start by looking at this graph in the datasheet. You can also see, by the way, that this one also seems to have a version that has a quadrature output, but this one is the sine cosine version. And you can see that it will output two signals. They will be on those two pins here. And you can also see that they are centered around 3/5 of VDD. And VDD here is 5 volts. And 3/5 of that is 3 volts. And you can see the peak-to-peak voltage of the signals is 2.2 volts or 1.1 volts amplitude. And that presents the first problem, which is that 3 volts plus 1.1 is 4.1 volts, which is more than you can apply to the pins of the STM. So you cannot give it more than 3.3 volts, so you have to get this voltage down a bit. The best way to do that would be to have probably some kind of op-amp circuit with a buffer that subtracts some voltage so that we center it at a lower voltage, because the amplitude is not too high, and the more amplitude the more signal integrity and the more resolution, so the better. I didn't have anything laying around that I easily can hook up with an op-amp, unfortunately, to do, so I just made a voltage divider on every output. I think I used two 10k resistors, so I just divide everything by 2. And probably if you want to go for the voltage divider approach, then you would not use two of the same, because you would want to preserve as much of the amplitude as you can, but it doesn't really matter. I just wanted to try to get it running. And you can see that I just took one of my motors that I, in this case, just used to spin the magnet that I just stuck to the back here, which is easier than spinning it by hand. And then I hooked it up to the COM port of the VESC 6. And to hook it up to the COM port, you cannot use the sensor port, you have to use the COM port for this one. And the sine signal should go to ADC 1, or I think it's just called ADC, and the cosine signal should go to ADC 2 if the hardware doesn't have a dedicated sine and cosine encoder port, which most of the ones based on the VESC 6 designs don't have. And we can, well, the USB is plugged in, so we can connect, and I can show that it works firstly. So what I had to do was to set the sensor port mode to sine cosine encoder, obviously. And if you do that, then you have to make sure that nothing is connected, no app is running, or not any app that will use the ADC inputs. And I think you can use ppm anyway, for example, but you can't use the ADC app or the UART app, because the UART app, I think the UART app runs on different inputs. So yeah, anyway, you cannot use the ADC ports for something else, so you couldn't use any analog throttle, for example, if you use this kind of encoder. And then once we have set up the sensor port, we have to go to FOC and the encoder tab, and here you have some settings for the sine and cosine encoder. And those are the offset and the gain for the sine, and for the cosine signal. And the gain is a bit non-intuitive, because it's called compensation even, and it's actually not the amplitude, it will be 1 over the amplitude, because it's multiplied by the amplitude before it is fed to the arctangent function. And if you want to see how to set them up, so what we have, the values we have here, you can see that VDD is, the offset is 3 volts, and we divided that by 2, so it's simply 1.5 volts roughly. So that's what I have set here. I can show you also exactly how I measured them. I made a Lisp script for that, so that makes it really easy. And then the gain compensation, you know that it should be 1 over the amplitude. So in this case, the amplitude is 1.1 volts, and we have divided that by 2, so it's 0.55, and 1 over 0.55 is a bit over 2, and that's where this number roughly comes from. And then if you go to real-time data and rotor position up here, actually I already have it running, so if you click on encoder you can see the encoder output. And first now when it's been sitting, you see that it's, yeah, the noise is around 1 degree or so, so it's not so bad. And that this is not with heavy filtering and with my crappy voltage dividers. And if I go over here and spin the motor, just turn it, you can see that it gives a nice angle estimate and seems to be working. And I think sine and cos encoders are interesting for a few reasons. So apparently they're quite common in some motors, that's also interesting. But one reason is that they don't take a lot of computations to run, because we're running the ADCs anyway, and it's just a bit of scaling and shifting and then using the fast arctangent function that also the VESC code uses. So you can get, it's not nearly as computation intensive as, for example, those SPI encoders that are, most of them are bit banged in the software. And another thing that is interesting, I think, is that you could run much longer cables on this one. I haven't confirmed this, but I think if you have good shielding, you're probably, nearly as limited by the bandwidth in the cable, because those are literally the fundamental signals, so you can, the signal will not degrade as much over a long distance. Those voltage dividers probably don't help at all here, because that increases the impedance, so it's better to go for the buffered solution with the op amps in that case, if you need to shift the voltage, which might not be the case for all encoders. And if you go for the resistor divider, it's probably better to put them close to the COM port, so that we have the low impedance for the longer part of the cable. And another interesting thing about them is that since they are sampled by the ADC that is triggered by the PWM timer, the sampling will be done at the same time as the current samples as well, so it will be nice and synchronized up to the rest of the VESC code. So yeah, it's nice that you can use them. Now I also want to show how I derive the calibration here. So if you go to VESC DevTools, and this is, by the way, in the beta version of VESC tool that I will try to get done in the beginning of December now. More or less everything is in there. I just want to test everything out a bit more. Then you can go to the, you will be in a terminal from the start. You can go to the Lisp tab, and then you can down here go to the examples, and then there's the encoder sine cos call calibration example. Then you can use upload or stream, and you can select poll data up here. And then you can see that I have a bunch of values that are plotted. And the thing that I'm trying to do in this example is to measure the maximum and minimum values. So I will just run a loop here and keep updating them as I get new values. So if we look at these values now and spin the motor, so what they have to do here, there's also a description, by the way, in the beginning on how to use it. So now if I turn the motor, you can see that these are updating. And I will keep turning it until they stop updating, because that means I have gone more than one revolution and I have gotten the minimum and maximum values of it, as you can see. And then from the minimum and maximum we can calculate all of these things. For example, the offset will be maximum plus minimum divided by 2, and the amplitude will be maximum minus minimum divided by 2. And since we want the inverse of that, then, or it will be divided by 2 is twice. No, it will be divided by 2, and we want the inverse of that, so it's 1 over that. And that's what I've done in this part here. And I did that individually for the sine and for the cosine. And you can see that we have the results down here. And you can see that they are similar, but they are slightly different. But if there are slight differences for some reason, then you can get them as well if you use this script. So I just did this, and then I went to FOC and entered the values here and wrote the configuration, and that was enough to get it working. And also about encoders, today I actually merged another pull request, which seems really nice, with the TLE 5012 encoder that also seems to be becoming popular. This is one of those SPI encoders. It takes a lot. This will probably be one of the more computation heavy ones, because it uses 48 bits to transfer all of the data, and it has some CRC calculations on. But you can use this one now as well. So That's another nice option. And compared to the AS5047, for example, this one has a shared data line for SPI that you can use to read data back even from the sense port, and then you can get feedback on if the magnet is too close or too far away, or if there's some error in the encoder and react to that. So that's also really nice. So those are some of the encoder updates and how to use a sine cosine encoder. Hope this was useful.